Hi students, in this first video for Online Lecture 7, we are now going to talk about two important periodic trends. The first trend is going to give us the basis set of the periodic table. So as the periodic table has been shown to you as a code breaker giving you many ideas as to not only the electron configuration, we are now going to use it to try and figure out not only the effective nuclear charge, but also the radius and size of our atoms. So what is the effective nuclear charge? It's the positive charge felt by the electrons in our atoms. So what we want to look at is what we typically call Z effective. Z being, in many cases, going to be our shielding constant. So in the case of our sigma, which is our shielding constant, we are going to look at Z, our number of protons in our atom, and try to balance how well those protons are able to hold on to all of the electrons in our atom. The greater our sigma, our shielding constant, well, that means that we are going to end up having a harder time trying to reach out and affect our outer electrons. So our Z effective historically can just be predicted as Z, our atomic number, minus the number of inner or core electrons. What does it mean to be a core electron? This means that it has a lower principal quantum number than our highest filled shell. So if we were to have electrons in the 4s subshell, then that means anything with a 3 and shorter is going to be considered a core electron. So let's look at some examples. In the case of our sodium, magnesium, aluminum, and silicon, notice that our Z increases by 1 as we are adding our protons. But then also notice that our core number stays the same because the electron that we are bringing in actually is going to be in the same subshell. This means that we are going to increase our effective nuclear charge as we are going horizontally across the row. So as you can see, this is going to decrease the radius because we are able to pull electrons closer when they have the same principal quantum number. So here is our general trend for effective nuclear charge. Effective nuclear charge is going to govern the other properties that we see not only in this video, but in the following video. So as we go from left to right, because we are filling up shells and subshells with the same principal quantum number, this means that we are going to have an increased effective nuclear charge as we are going from left to right in our horizontal rows. As we go down the periodic table, however, we are going to put our electrons in orbitals farther away, increasing the number of core electrons and shielding electrons that we have. So we are going to see a decreased effective nuclear charge as we are going down the periodic table. As a point of note, you may go online and look and see that they will say that the nuclear charge increases as you go down the periodic table, and that is true because you are increasing the number of protons. However, the reason that the effective nuclear charge decreases is that you have more shielding electrons in the way, making it harder for those valence outer electrons to be pulled in by the addition of those protons. So what does this do for us? Well, now we can look at our atomic radii. The metallic radii are very easy to determine because we are going to look at our radius as more or less just 1/2 the diameter of the atom. How we would do this is look at our atom as two adjacent species. Those would be the nuclei. So then what I can do is measure the distance in between those 2 points on our atoms. And we can say because they are the same metallic atom, we would be able to get the diameter, which then we figure out is just the radius of 2 atoms side by side. So it was very easy to determine the radius of our metallic atoms. For our covalent atoms, however, much more difficult. The reason why is that there is going to be orbital overlap, which we are going to see with the covalent bond here in the next couple of chapters, and you'll notice that the atoms are a little smushed together. So what happens is that you're actually going to predict a radius that is actually slightly less than what you would expect in a free atom by itself. So what could we do? Well, what we ended up doing is starting to mix these atoms with various other atoms to form ionic compounds in which we could see our different species. Then we could do some predictions, or we would mix them with other atoms and we would start to take a statistical average. So let us take a look at our periodic trend. Notice that as we go down the periodic table, our atoms are going to get larger. This is because our electrons are going to get further because we're populating further out orbitals and we have less effective nuclear charge. As we go from left to right, the overall trend, for the most part, is that the atom is going to get smaller. This is because we see an increase in the effective nuclear charge, which means it can pull those electrons much closer, and that results in a smaller atom. So as you go down a family, we expect them to get larger. As we go across the periods, as you can see here with lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, they are going to get smaller. This is a typical trend that we expect for you to know. Now you can also see what will happen with the transition metals. So one of the issues in our last example is that you'll notice that the transition metals were not put in those estimates. So what we can do is now look at the trend of those transition metals. So where those can be found very easily is notice that you will see a grouping right in here. Here are our transition metals. They historically get smaller, but notice that when we start to pair up electrons in the d orbital following Hund's rule, they start to get a little slightly bigger. As you can see here with our rubidium, notice that we are going to get the same type of decrease to start off with, and then as we start to pair up, we are going to have repulsion and the atoms slightly get bigger. So as you can see here, here is my last group of my transition metals. But now becomes the question of what is going on here with these two little peaks that we see here. This is actually going to be our lanthanide series right here. So our lanthanides are actually fairly consistent, except for when we start to repel, notice that that one repulsion of an electron causes a fairly noticeable shift in its size. So my circled groups that are unlabeled are going to be the transition metals, which historically will decrease in size following the rules of effective nuclear charge. But upon pairing up of our d electrons, notice that the atoms start to get bigger. So let's look at this example for this video. Order the following elements in descending order of atomic radii. I want to go from the largest to the smallest. So in this case, I have antimony, bromine, chlorine, germanium, and sulfur. So now we have to go and look at the periodic table and be able to see which ones are going to be easily compared to each other. So let us go bring back our periodic table. The first one that we have is antimony. That is number 51 here as SB. So if we have SB, we also have our bromine. Then we had chlorine. We had germanium. And finally, we have sulfur. So here are the 5 elements that we are trying to compare. So the first one that we should probably start with is our antimony. Notice that it is a full row farther down than any of the elements that we are comparing. Because it's in a fairly similar location, because it is farther down a row, we would expect this to be our largest in the group. So now what we can do is look at the next row up above. We must compare our germanium and our bromine. So between the two, which one would we expect to be largest? Remember that as we go from left to right inside of our rows, we expect our atoms to get smaller. So in this case, we would expect our germanium to be larger than that of our bromine. If we also look at our sulfur and our chlorine, we would expect that to be the same as well. So we could probably get a really good prediction of this looking at our periodic table and say that we could go from antimony to germanium to bromine to sulfur to chloride. So let us go and see if we have that in here. If you'll notice, we have two possible answers of our antimony being first, and then you will also see based off of here that answer A follows that exact order that we had on the last slide. This means that we would have our antimony be the largest, germanium would be next because it is left of that of bromine, and our sulfur is left of our chlorine, and this is the descending order that we get. If I had asked for them in ascending order or getting larger, then what we would do is end up flipping this and going from the other direction. In this video, you saw how important it was to look at the periodic trends of our effective nuclear charge and our atomic radii, which more or less comes from the effective nuclear charge. In the next video, you're going to see a couple of other trends in which we use the effective nuclear charge to figure out what we are going to do with electrons. Have a great day.